Welcome to the last week of AA203. So from our usual roadmap, we're always for the last few weeks, we have been in the top right quadrant of our roadmap, specifically looking at learning-based methods for optimal control. And over the last couple of weeks, we've basically been introducing the reinforcement learning setting, where we are looking at ways to estimate value functions. Specifically, we introduced Monte Carlo and temporal difference learning as like really fundamental model-free learning strategies. And last week, we also looked at one of the kind of families of methods for model-free reinforcement learning, namely value-based methods. On the other hand, today we switch topics and we kind of complete, if you wish, and start to discuss the second main family of methods that belong to the model-free reinforcement learning family, namely policy optimization. And as we will see today, in policy optimization, differently from what we did in value-based methods, whereby the policy is implicitly defined through the value function itself. In policy optimization, we'll see how we will be representing the policy explicitly, namely through a parametric representation of the policy, and then tune or adjust the parameters of this parametric representation of the policy to directly maximize the reinforcement learning objective. But long story short, today we'll be looking at policy optimization methods. Specifically, we'll start by introducing and defining policy gradients, which will lead us into kind of the very first algorithm, which will be the reinforced algorithm, and we'll discuss some we'll do some discussions on the role of variance of these policy gradient estimators. Then we'll be looking at actor-critic methods, which are extremely popular instantiation of policy optimization, and then conclude with some mention to kind of recent reinforcement learning algorithms and applications. Okay, so let's start from, if you recall, at the beginning of our discussions on reinforcement learning, we loosely introduced kind of reinforcement learning as this, as a problem where we have an agent that interacts with the environment. Through this interaction, we generate some trajectories tau, which are nothing else than kind of sequences of states and controls that we observe over time. And we, through this, we defined kind of the formalism for reinforcement learning as a Markov decision process, whereby we defined a trajectory distribution, P of tau, where P of tau essentially encodes all the stochasticity that we have in the environment. Namely, we could have an initial state x0, which is sampled from a distribution over x states. Concretely, this could be like the dot reset method in our gym environments, for example. We have uncertainty that comes from the policy itself. So we are defining a policy pi as a distribution over controls given states. And so this in itself is also a random process. And then we obviously discuss also the stochasticity that comes from the transition function itself, which is a distribution over next state, xt plus 1, given the current state, xt, and the control, ut. Right? And so by taking all of these sources of stochasticity and factorizing them, as was shown here on the slide, we basically derive the probability distribution over all possible trajectories tau as this factorized distribution over here. Why was this important? It was important because this enabled us to define the reinforcement learning objective, essentially as a maximization problem, where we want to take the, basically pick the policy pi that maximizes a certain objective. And this objective is the sum of discounted cumulative rewards. But this sum of discounted cumulative returns is an expectation where the expectation is under this trajectory distribution. Right? So this is basically where we started a couple of weeks back. How does policy optimization go for solving this problem? As we were briefly mentioning before, in policy optimization, what we do is we essentially define our policy to be a parametric policy, pi of theta, with some parameters theta. And therefore, kind of the reinforcement learning objective can, and the trajectory distribution itself, can essentially be written with respect to these parameters theta, right? So the initial state distribution and the transition distribution do not depend on theta directly, but our policy does indeed inform the evolution of the trajectory. And therefore, what we want to pick essentially is the values of the parameters theta that maximize the RL objective. So long story short, at face value, in policy optimization, we take the reinforcement learning objective as it is, and we basically define it as an optimization problem with respect to the parameters of our policy. Again, going forward, to simplify the notation, we will assume that this is an undiscounted environment, but everything still holds when we actually account for discounting. So let us start solving this problem in practice, right? So we saw how well, in value-based methods, if you remember, we were ideally solving this exact same problem, but we were doing this in an indirect way because we were doing essentially fixed point iteration on Q values and value functions. And then we saw that at convergence, we derived some theory, or at least mentioned some theory for which kind of the algorithms that we proposed would converge to the optimal value function and therefore to the optimal policy. In reinforcement learning, now we want to solve this kind of explicit optimization problem. So we know that before in this class we mentioned as a good idea when we want to solve optimization problems that gradient ascent or gradient descent is a good approach for solving a general class of numerical optimization problems. Fundamentally, if we were to approach this problem through gradient ascent, because we want to maximize this objective function, we would need to, first of all, estimate the gradient of the objective we're interested in, and then basically cast learning, or learning the policy, as doing gradient ascent on the objective that we care about. That is, iteratively take steps in parameter space following the direction that is given to us by this gradient, right? So pictorially, hill climbing our RL objective. Kind of a first question here is already kind of, we see how our objective that we wish to optimize is a non-trivial object, right? Because we have this expectation under the trajectory distribution, which is something which we don't really know about. Because the trajectory distribution, as we said before, kind of has these three sources of stochasticities. So we can assume that we know our policy, and we can evaluate the distribution under our policy, but we don't really know the transition dynamics, for example, right? Because this is the whole point. So, first question is, how can we even evaluate this expectation in the objective? And the answer here is by basically leveraging the same tools that we discussed over and over the last couple of weeks, which is essentially sampling, right? So in reinforcement learning, whenever we don't know some quantity, for example, the transition functions, we kind of go around it by sampling in the environment. What did we mean by sampling so far? It's essentially taking rollouts and interacting with our environments over time. So in other words, we have this objective that we wish to optimize, which entails computing the expectation under the trajectory distribution. We don't know how to compute this expectation, and so we can approximate it by running our policy n times in the environment and just taking the empirical mean. Right? So in practice, you could imagine indeed following n possible rollouts of our policy. These rollouts will have some rewards. We will be observing different quality of these rollouts, and then we simply average out all of the rewards that we observe over time. And this would be a valid approximation of this expectation. Okay, but so we mentioned that we want to approach this through stochastic gradient ascent or gradient ascent. The first thing that we need to do is compute the gradient, right? So what we'll do right now is basically derive the policy gradient and specifically derive actionable expression of the policy gradient, and then see how we can use this expression within kind of working algorithms. Any questions so far? Great. Okay, so for compactness, let us define R of tau, of the trajectory tau, as the sum of rewards that we observed in a specific trajectory. So simply the sum of all the rewards observed from time 1 until time t within that trajectory tau. So we can use this r tau to basically rewrite the RL objective that we were introducing before, right? So J of theta, which we introduced before as being the expectation under the trajectory distribution of the sum of rewards, we can just write it as small r of tau. And by definition of expectation, we can write this expectation as the integral of p tau times r tau in the tau. So what we said is we want to take the gradient of this objective function and use this to hill climb. So given this definition or kind of rewriting of the objective J of theta, the gradient of J of theta with respect to theta is the integral of the gradient with respect to theta of p tau times r tau in the tau. Right? So nothing special here. We rewrote our RL objective, and then we're taking the gradient at face value of that objective. So here, of course, this would not be actionable, right? Because we would like to evaluate this gradient and basically take a step in the direction of that gradient. But the problem here is that how we defined it right now, basically the gradient depends on unknown dynamics and the initial state distribution through the probability over trajectories p tau, right? So this is still the object that we don't really know how to compute. So here will be essentially what we'll be doing in this slide and the next is that we'll be basically massaging this definition of the policy gradient until we derive an analytically tractable and actually computable expression of that same gradient. So the first thing that we do is we realize that this is the object that is creating problems for us. And so we leverage that identity on the right of this slide. Specifically, the identity whereby the probability p tau times the grad log p can be rewritten as the grad p's, essentially. Right? So we know that the grad of the logarithm of a function can be essentially written as the gradient of that function divided by the function itself. And so the two terms cancel out, and so we get that kind of useful identity on the right. So specifically now we can do this substitution in our expression of the policy gradient, and what we get is that we get the integral of the p tau times the grad log p's times r tau, always in the tau, of course. Now again, we can use the definition of expectation, and we can basically rewrite this integral as the expectation under the trajectory distribution of this part over here, right? Now this is not actionable yet, because still we have this expectation, and this term here is not something we know how to deal with. But you can probably start to see that we are somehow on the right track, because we know that whenever we have some quantity that is defined as expectations under the trajectory distribution, we can just approximate this expectation through interactions with the environment and through sampling. So this is one step in the right direction, but still not completely actionable, because we have this grad log p's in the equation, which is still something we don't know. Okay, so let's keep going. So let us recall, from the previous slide, the definition of the trajectory distribution, right? Which is basically this factorization of what for us is the trajectory distribution. If we take the logarithm of the trajectory distribution, products become sums. Each individual terms becomes of course, we take the logarithm. And basically what we get is the log p's is equal to the sum of these three terms over here, right? So the logarithm of the probability of the initial state plus the sum over time of the log pi's, essentially the logarithm of the distribution induced by our policy, and the log p's, that is the transition dynamics. So we just substitute this into our equation of the policy gradient, and we get this object over here, where Yes, so we are taking the gradient with respect to theta of this entire term here, which we derived as the logarithm of the probability distribution of trajectories multiplied by the sum of rewards in that trajectory. Now, of course, notice that since we're taking the gradient with respect to theta, the first and the third term here don't depend on theta directly, so they don't contribute to our gradient. And notice that the only term that remains is actually something that we know how to compute, right? Because the policy is an object we define. For example, the policy for us might be a Gaussian over a one-dimensional continuous action, right? So we could have our u of t, and so our policy pi of ut given xt might be a Gaussian, where the parameters theta might represent maybe the mean and the variance of that Gaussian. And so basically the log pi's are completely specified, and so we can actually evaluate them. And so this means that if we take that expression over there and just rewrite it compactly over here, where the only thing that changed is that we re-expanded our terms small r of tau, we see that we get an expression of the policy gradient, which is something where, first of all, everything inside this expectation is known. So this is just the sum of rewards that we observe according to some trajectories tau. This is the sum of the log pi's according to our policy, which again is something we know how to compute. And so everything inside this expectation is known. Do these steps make sense? Or any questions until now? Okay. So we said that everything inside this expectation is known. How do we evaluate this in practice? We use the same trick, right? So we have this expectation under the trajectory distribution. We know that we can approximate this as the empirical mean by basically sampling n rollouts in our environment. We did this before for the objective, so we can do exactly the same with the policy gradient, right? Which basically means that we can now completely evaluate the policy gradient that we're interested in by taking n rollouts or trajectories, basically taus in the environment, computing this quantity for all of these trajectories and taking the mean. And this would be a valid approximation of the policy gradient. Okay, and so basically, if this is clear, through this derivation of the policy gradient, this leads us directly into, if you wish, kind of the very first policy optimization algorithms that we will see in this class, which is also known as the reinforced algorithm. So as you can probably imagine, the derivations that we derived so far basically give us an actionable strategy. Because now what we can do is something along the lines of these three steps over here. So we will be sampling n trajectories from the environment by basically just letting our policy interact with the environment itself. Through these trajectories, we can now always evaluate these gradients or the policy gradient, or at least approximate it. And once we have this estimate of the policy gradient, we can take a step in the parameter space according to this gradient to improve the basically the quality of our parameters theta that represent our policy pi. So taking the bird's eye view on this reinforced algorithm according to our usual skeleton, we have our usual three components, whereby we are generating samples by interacting with the environment. We are estimating a return through Monte Carlo, because we're basically running our policy in the environment and explicitly summing up all of the rewards that we observe at the end of our episode. And then we're using those estimates of the returns to improve the policy namely taking a step in parameter space. Of course, kind of this is, if you wish, like one step of an inner loop, whereby we would then have to repeat this over time, right? So here we're taking one gradient step, but then you can imagine that we have outer for loop that is kind of wrapping these three steps where we repeat this process. Because now we would have an improved policy with some new parameters theta, which will collect new experience, and we'll use this experience to re-estimate the gradient and keep iterating over time. Okay, but let's stop for a second and kind of try to build some intuition into what policy gradient is actually doing under the hood, and indeed get some intuition behind the math, which I think is always useful. So we did all of those kind of algebraic steps to basically derive this estimator for the policy gradient, right? We explained before how the log pi's essentially represent the log probabilities of the action according to our policy. And we saw before how this could be represented either in the continuous space, exactly as we were doing here on the slide, but this is equally holds if we're looking at a discrete action space, whereby, namely, the policy will be expressing a categorical distribution over a finite element, a finite set of actions that we could pick. And so this is basically the term that we derived. But I think it's useful to compare it with the expression of the gradient that we would get when we try to perform maximum likelihood, or if you wish, kind of behavior cloning for us for the purpose of control. So remember the setting of behavior cloning. In behavior cloning, we have some demonstrations of an expert doing something and executing a task, which for us namely means data sets of tuples of states and action pairs, which basically are examples of this mapping that we wish to approximate, right? So we want to, in maximum likelihood estimation or behavior cloning, what we wanted to do is we wanted to maximize the probability of the actions that we observe from our expert given the state, right? And so formally, the gradient in the maximum likelihood case would essentially be comprised of this term, where we're trying to maximize the probability of the actions in our data set, because this would essentially be equivalent to approximating the behavior of the expert, right? If you compare this equation of the gradient to what we just derived for the policy gradient, you see that this is essentially a weighted version of the gradient that you will get from maximum likelihood estimation, where the weight is specifically the sum of rewards in that trajectory. So what does this mean? Is that in behavior cloning, we kind of taking a step in the direction of the gradient essentially means upweighting the probability of all the actions in my data set. In policy gradient, we are upweighting the probability of the actions according to their performance in those rollouts, right? So those actions that led to higher reward are more upweighted in my policy gradient term, and so we are upweighting that probability, if that makes sense. Is this clear? Does it make sense? Indeed, and so the policy gradient is a weighted version of the maximum likelihood estimation gradient. So again, kind of to hammer down this idea, if we take a step in the direction of the policy gradient, what we're doing is that we're changing the parameters theta such that trajectories with higher reward have higher probability, right? And so you could imagine if we have like this fictitious landscape of rollouts where the width of the lines here represents the probability mass that my policy is allocating to those trajectories. Then here, what we want is we want the good trajectories to be more likely than the bad trajectories, right? And so, in a way, policy gradient really formalizes this idea of learning by trial and error, because we are running out, kind of getting rollouts of the policy in the environment. So we're trying out different strategies. And then through basically updates in parameter space, we are learning what is more effective and making it more likely. And we're learning what is less effective and making it less likely. Yeah.
In learning context, we couldn't use this approach because we don't have an explicit formulation of the reward. Is that kind of why? Or?
I would say, so yes, for example, you might not have an explicit measure of the reward. I mean, you could construct it and then maybe reweight your behavior cloning loss, for example. So this is something that, if you recall, we did discuss towards the end of the behavior cloning class, where we looked at, so we refer to them as reinforcement via supervised learning methods, where we did have a notion of reward, and maybe we use that to filter demonstrations or whatnot. But so at face value, yes, so this is the reason why. Okay, and so I would say this is probably the most kind of fundamental idea for this lecture. So we started saying we want to approach the reinforcement learning problem from a slightly different angle, that is the one of policy optimization. So we parameterize our policy, and then we cast reinforcement learning as an optimization problem with respect to these parameters of the policy. And to do this, we do gradient ascent. And so everything that we've done so far is derive the expression of the gradient. So, of course, this is not it. There is much more to policy optimization, in the sense that what we discussed so far is great. And from an intuitive standpoint, it also makes a lot of sense, at least to me personally. But I would say that kind of if you look at this gradient, there are some clear limitations. And I would say the main one is the fact that this gradient, our estimate of the gradient has extremely high variance. And so this is an extremely, if you wish, unstable learning signal to follow. But so let us now spend a few minutes on this problem of high variance of the policy gradient. And so what we'll do now is we'll first briefly build some intuition to why this high variance might be happening. And then we'll look at two strategies for reducing the variance of the policy gradient. So, consider this, again, kind of fictitious example here on the slide. Specifically here, we are kind of visualizing, if you wish, like on the x-axis, the space of trajectories. So all possible trajectories that we may follow according to our policy. And this Gaussian here is basically represents a distribution over trajectories induced by our policy pi. Now, say that we basically run our policy in the environment and we observe 3 trajectories. And these 3 trajectories have some associated return, right? So we have these 3 trajectories, we sum up all of the rewards, and we obtain these 3 specific performances. Now, out of these 3, 2 of them were positive in this direction, and 1 of them was actually negative. Now, from everything that we've said so far on policy gradient, well, we would expect policy gradient to do is that if we then use these trajectories, estimate the gradient, and take a step in the parameter space, what we're doing is that we're making this behavior more likely than this behavior here, right? Because this is exactly what we've been discussing so far. And this is actually what would happen. But now let's suppose that we take those same 3 trajectories and simply add kind of the same positive constant to the returns to get these 3 new values, right? So the relative gap is always the same, but what changes is the kind of absolute numbers of those rewards. The catch here is that if we now would do the exact same thing, that is policy gradient on these trajectories, what we will get is something slightly more dispersed. So because this is also kind of a positive number in this case, policy gradient will still try to, well, it will try to, of course, give more likelihood to the better ones, but it will still try to cover kind of this trajectory over here. And so, of course, this is, if you wish, like an extreme example. But the main idea that I'm trying to convey here is that because we are estimating the true value of the policy gradient through samples, depending on the samples that we observe, the policy gradient can vary also quite substantially, right? And so this is exactly what we mean that the estimator that we came up with of the policy gradient has a high variance. Why do we care about this? It's because in practice, if our estimator of the gradient that we follow for learning has high variance, this will essentially lead to worse performance, slower convergence, and potentially more unstable training curves, essentially. So within kind of this framing, I would say that a lot, if not the majority, of the research in policy optimization essentially revolves around finding ways to lower the variance of these estimators. And so different algorithms essentially boil down to instantiating the policy gradient in different ways. Any questions on this? Yeah.
So rewards can be discrete or they can be continuous and provided benefits. Does providing like a more clear gradient decrease the variance of the policy gradient? Is that the right interpretation?
Sorry,
compared like you got like a goal point, let's say, and like you reach the goal and you get 5 points.
Yeah.
Versus like you get points based on your proximity to the goal. It's a continuous signal. Does supplying a continuous reward signal decrease the variance of
yes, I would say that in general, like the more dense your reward is, the better it is for propagating the learning throughout the algorithm in general. Yeah. Now it's not only because of the variance of the policy gradient, but I would say in general also for kind of credit assignment, right? So if it encodes learning to be more granular throughout your entire trajectory, if that makes sense. But yes, your intuition is correct. Okay, so let's look at a couple of strategies to reduce the variance of policy gradients. So the first one, I would say it's more than a simple trick than an actual strategy. In the sense that if we look back at what we're doing to define the policy gradient, we essentially defined it as, of course, the empirical mean because we want to approximate the expectations. We have this first term, which is the log pi's. Great, something we can compute. And we were weighting the log pi's by the sum of rewards throughout the entire trajectory. Now, if you look a little bit more closely into what this is doing, is that it may happen that for time t prime greater than t, kind of the log pi's of this t prime would still be weighted by the sum of all the t's before t prime, which is something counterintuitive, right? Because basically the policy at time t prime cannot really affect the reward for the time steps before that action, right? And so this is what I mean by causality here on the slide. And so the first trick essentially entails leveraging this intuition for the fact that actions at time t prime cannot affect the rewards that happen before it, and simply encode this into how we are defining the policy gradient. So rather than, so right now, kind of here, I'm just taking out this summation to make it more explicit. But so rather than summing from t equals 1, what we would be doing here is summing from t prime equals t, specifically. So this makes sense intuitively, but why does this lower the variance? So first of all, of course, we're not including a lot of terms on which the action doesn't really have any influence on. And then also, I would say quite intuitively, we are summing less terms in our policy gradient, right? Less terms of the reward. And remember that the reward is essentially something that depends on a number of stochastic elements throughout the trajectory, right? So again, throughout the trajectory, we will be sampling repeatedly from our policy, which is indeed something stochastic. We'll be sampling repeatedly from the transition function, which is also something stochastic. And so, simply put, here we're summing less terms, and so there is less variance associated with this policy gradient overall. Does this make sense? This is pretty simple trick, I would say. But it does indeed measurably improve things. The second strategy, which I would say is very important for for the space of policy optimization methods, is the one of introducing the concept of baselines. So to understand exactly what we mean by baseline, let's reconsider kind of the intuition we were discussing before regarding policy gradient, when we were saying that policy gradient makes good behavior more likely. And so, and specifically what we're discussing is that policy gradient will only do kind of quote unquote the right thing if the returns, that is the sum of all the rewards that we are observing, were centered, right? So we specifically consider this counterexample on the right where the relative difference was the same, but simply those returns were not centered. And so the policy gradient was actually doing something that we didn't want it to do. Intuitively, what we would like to have instead is that we would like to use some mechanism to center our returns such that the policy gradient essentially becomes something whereby the probability of behavior that is better than average gets increased, and the probability of behavior that is worse than average gets decreased. So in other words, we want to have a mechanism to recenter the returns from our interactions with the environment. The way we'll do this is through something that is referred to as a baseline, here referred to as B, which is basically a quantity that we are subtracting to the sum of reward, to the return R of tau. So before we get into kind of actionable ways of using the baseline, I think kind of a valuable sanity check here is, so we're introducing something in the policy gradient. We don't want to change the expectation of the policy gradient, right? Because we derived kind of our equations analytically, and we know that in expectation the policy gradient will, to the limit of infinite samples from our distribution over trajectories, we'll get the correct object. But now if we subtract this baseline B, do we still get the same expectation, right? Is the estimator still unbiased, essentially? And so the claim here as a spoiler is that adding this baseline does not change the value of the expected gradient. And so let's look at this more closely. So to understand this, let's consider the following expectation. So specifically, let's look at the part of the policy gradient which only takes into account the baseline. So the grad log p's times the baseline b. Again, from the definition of the expectation, we can rewrite this as the integral of p tau times the grad log p times the baseline b. Right? So here just a definition of expectation again. And now we can use the exact same identity that we used before in the derivation of the policy gradient, but now in the reverse direction, if you wish. So we can basically take the p times grad log p's, which is equal to the grad p's over here, right? And so this entails to grad p's times the baseline b. Now we can take the b, because this is just a constant, out of the integral. We can do the same with the gradient operator. And so what we get is the b multiplied by the gradient of the integral of the probability over tau in the tau. since the probability distribution over trajectories is a valid probability density, we know that the integral has to be equal to 1. And so what we get is we get b times the gradient of a constant, which is equal to 0. And so this basically makes the estimate of the gradient with the additional baseline term still unbiased in expectation, right? Because here we basically verified that the expected value of the term that we are subtracting is equal to 0. And so we're not really changing the actual expectation of our estimator. Okay, which I think is something pretty neat, right? Because basically now we have this mechanism through which we can recenter the returns in our policy gradient and therefore reduce the variance, basically for free, right? Because we're not really losing anything in terms of bias of our estimator. Since what we say is that the goal here is to center the returns, a pretty effective and popular choice of the baseline is actually to define the baseline as the average return, right? So remember, again, here we are interacting n times with our environment, so we have n trajectories tau. For all of these trajectories, we will have some return, and so we just define b as the average return over our trajectories. We'll see how this idea of average returns basically motivates many popular reinforcement learning algorithms. But for now, I would say this is kind of the intuition that we are trying to capture, right? So remember what we're doing here. We are interested in using policy gradient-like algorithms. We recognized that the policy gradient is a high variance object. And so we want to reduce this variance through baselines. And here we basically showed one way of doing so. Any questions on this? Okay. What does it mean in practice to have a baseline? Again, this is just kind of a simple example of training curves. But to give you an idea is that in practice, what this would mean is that even for very simple environments, you would get much faster kind of training for the exact same algorithm when you're just changing the expression of the policy gradient, right? So here we're basically looking at it from the perspective of maybe sample efficiency, so you converge faster. But in some cases, this actually makes a difference between converging or not converging to a good solution. So basically, this is what I mean when I say that the quality of the estimator of the policy gradient actually influences training quite substantially. Okay, so let's take a step back and think about what we're doing, right? So everything that we've done so far today is basically defining a different way of solving the reinforcement learning objective. First of all, we express it as a function of the parameters theta of our policy. We evaluate the gradient of that objective. We saw how to do it. And we take a step in parameter space according to this gradient. Now, given basically this high-level structure, if you recall, last week we were discussing the differences between on and off policy algorithms. Specifically, we mentioned that an on policy algorithm is an algorithm that uses experience collected under the policy that we are using to explore the environment to improve. Would you say that this is an on policy or off policy algorithm in this case? Yeah. Yeah, exactly. So this is in this specific framework, as we've seen it so far, policy gradient algorithms are indeed naturally on policy, because the estimate of the gradient depends on basically the rollouts that we did in the environment according to the current policy pi theta. The moment we update the policy, we'll have to collect new experience in order to re-evaluate the policy gradient for that policy. Of course, there are extensions of policy optimization. So the takeaway here is not policy optimization algorithms are on policy, but there are, for the way we derived it so far, these are indeed on policy algorithms. And indeed, exactly as we said, it is on policy because we need samples from the current policy to estimate the gradient. So let's look a little bit more closely at a couple of pros and cons of policy gradient methods. First of all, I think it's nice to point out how policy gradient methods naturally handle continuous action spaces. And this is because basically all we have to do is we have to define an appropriate representation of our policy, phi of ut given xt. For example, this could be a Gaussian, and we parameterize the parameters of that Gaussian. So same thing if we were to use a discrete distribution, so a categorical distribution, we will be essentially able to leverage the exact same formalism, regardless if the action space is continuous or discrete. On the other hand, in value-based methods, if you recall, kind of the policy for us was basically implicitly defined as an argmax over u of, for example, a q function, right? Doing this argmax is obviously easy in the moment in which this is the action space is discrete, so we have a finite set of values for our actions u. The moment u is a continuous object, then this in itself is an optimization problem, right? So which might or might not be trivial. Same caveat here. There are, of course, methods that allow value-based methods to be applied for continuous action spaces, but at face value, this is a clear distinction, right? A second pro is that by how we derived it, policy optimization methods directly optimize the objective we care about, which is the discounted sum of rewards over time, right? So we are clearly differentiating between policy optimization methods that take the RL objective and optimize this objective at face value. So we literally do gradient ascent on that objective, from value-based methods such as Q-learning, which derive a mechanism, for example, the Bellman optimality equations, to enforce a kind of a fixed point iteration scheme that at convergence will also lead to optimizing that same objective. But for intermediate solutions, it's not really clear if there is a partial ordering, right? So for policy optimization methods, since we're doing hill climbing, if we stop halfway, we probably have a good estimate of how much we have been improving over time. On the other hand, with Q-learning, we know that we have guarantees of convergence, but if we stop halfway, we don't really know kind of how we are with respect to previous versions of the policies we computed. Yes?
For Q-learning, like stop halfway.
Yes, so in both cases, remember that we're looking at like sequential iterative algorithms, right? So here, this is basically gradient ascent, which we take sequential steps. In Q-learning, we are basically doing fixed point iteration. So we are recursively enforcing maybe the Bellman optimality equation. In both cases, you might stop before convergence. In policy optimization case, I would argue it's pretty clear to understand progress because you're maximizing an objective. In Q-learning, it's less clear how to value, to compute or evaluate progress in between before you reach convergence, right? But I would say kind of the bottom line here is that in value-based learning, we are introducing kind of an intermediate objective to achieve the same thing, while in policy optimization, we say we want to optimize the RL problem, and we just do that. The con is that at face value, at least the kind of algorithms we just discussed are on policy, compared to, for example, Q-learning, which might be prone to off-policy learning as well. And so on policy, in this case, can be extremely sample inefficient, whereby we essentially mean that we might have to interact with the environment many, many times before we actually converge. Okay, any questions so far before we move on to actor-critic methods? Okay, and so let's now look at actor-critic methods, which build, I would say, quite substantially on all of the ideas we introduced so far, namely the policy gradient. But I would say at their core, actor-critic methods try to blend and kind of leverage the best of both worlds between policy gradient methods and value-based methods, and we'll see shortly how. So specifically, consider again the policy gradient expression we just derived, right? Which is again kind of the sum, so the average of the sum of the log pi's times the sum of the reward of our trajectory. The sum of rewards from time t up until capital T is also referred to as the reward to go, because essentially encodes all of the rewards that we will be seeing in the future of our trajectory. And in a way, basically, all of the discussions of the high variance of the policy gradient that we were doing before essentially boiled down to the fact that this reward to go is indeed the part whereby we have that is basically contributing to this high variance, right? Because this reward to go, we only have kind of a limited sample estimate of what the expected reward to go is. And when we actually sample from the environment, this might only be kind of a noisy estimate of the ground truth expectation we're interested in. Why is this a noisy estimate? It's because, again, as we were saying before, we are basically repeatedly sampling from various sources of noise. And so even if we were to take the exact same sequence of actions over time, we might end in slightly different rollouts of in our environment. So kind of I would say actor-critic methods at kind of fundamentally say the following. So rather than estimating these expected rewards to go through sampling, whereby sampling basically entails just evaluating rollouts of our policy in the environment, why don't we try to estimate the actual expectation by fitting, for example, a parametric representation of that, a parametric function to basically estimate this ground truth expectation that we care about. And so at a high level, what actor-critic methods do is that they define two parametric functions that we are interested in learning. The first one is the actor, basically our policy, so our policy pi of theta. So we have some parameters theta that we wish to estimate, as we were doing so far. But they also introduce a critic that is basically a mechanism to estimate more accurately the expected reward to go that we would like to have. How do we do this? This is basically everything that we have been doing so far in the last couple of weeks, which is basically we want to estimate the value functions, right? And so we saw before already how we can use, for example, parametric approximations to estimate and approximate value functions, right? So very high level, what actor-critic methods do is that they recognize that part of this high variance problem that we see in policy gradients basically is caused by approximating the reward to go through samples. And so instead of approximating this reward to go to samples, let's fit a parametric approximator of the ground truth expectation, which, assuming we're able to do correctly, then this will reduce the variance of my policy gradients. So putting this together, instead of multiplying my log pi's by the sample return, as we were doing over there, so our reward to go, let's replace the reward to go with an estimator of, for example, a value function. with some parameters phi. Does this make sense? Okay, and so if this is clear, so this is, this is a good idea. So let's just fit a parametric function to our value functions. Can we combine what we're doing, so this idea with the discussion on baselines that we did before? Well, the answer is yes. So let us try to reduce even further the variance of our policy gradients by basically taking our new estimate of the policy gradient, where we are using our fitted Q function, and let us add the baseline again. Exactly as we were saying before, kind of the intuition that we tried to leverage in the baseline is that we wanted to center our returns. And so in this case, to center kind of our value function here, we could pick a state-dependent baseline, B of xt, that depends on states xt, which is basically the expected Q function value. Right? So here we're basically doing the same thing. We want to center this quantity. How do we center this? Well, we could pick B as the expected Q function, where this expectation is taken under the distribution over controls ut according to our policy. Right? So even if the exact details here are slightly unclear, I would say the main idea here that we want to take home is that actor-critic methods introduce an estimate of the value function to better approximate the rewards to go. This is great. Can we combine this idea with baselines? Yes, we can do that. We said that with baselines we wanted to recenter our reward to go term. We can center this by picking the baseline in this way, essentially. Now, let's look at this term a little bit more closely. The expected Q function under our policy is basically nothing else than the value function itself. So this is something that can be somewhat confusing at first, but let us try to look a little bit more closely with an example. So consider a discrete environment, again, for example, a grid world, where we can take maybe one of a finite number of actions, right? So we know that the Q function, in this case, under some policy pi, is basically the expected reward that we expect to have in state x, taking action ut, and then following the policy pi for all the time steps that come, right? So this is the definition that we had so far of the Q function. Where specifically, you see that here we are basically picking the action ut because the Q function is defined over this tuple, right? States and controls. How can we connect the Q function with the value function for that same policy? Is that intuitively the value of a state is the average value that we will get of the future states, where this average is taken under the kind of the probability distribution that decides which action I'm picking right now, if that makes sense. So this value function here is basically averaging out the future values according to all the possible controls that I might pick in that state. Does this make sense? Yeah.
where you're like looking over all possible states or like or actions in the future, and then like you just said, averaging them out at the time. Okay.
Yes, I would say the intuition is very similar. So maybe one other way to see this is temporally, right? So basically, the only thing that changes is the one-step reasoning that we're doing, because from t+1 onwards, we're still sampling from our policy. And so we are averaging out over all possible things that could happen over our policy. In the one step, so from t to t+1, the Q function is basically has one information more, which is we are specifying what control we're taking right now, right? So we're basically committing to one specific action, right? On the other hand, the value function is a function only of the state. And so what we're basically saying is that the value of this state, if we don't know which action we're picking in this state, will basically depend on the average action that we're picking in this state. And so the average action is sampled according to our policy. If that makes sense. Okay, so this is just basically a small detour, but I think useful to figure out what we're saying here. So here we're looking at introducing the baselines. We mentioned that this was a reasonable choice of a baseline. We now just saw how the expected Q function is nothing else than the value function. And so we can then rewrite the expression of the policy gradient as, again, the average over n trajectories of the grad log pi's multiplied by our critic estimator of the reward to go minus the value function, which in this case is the policy, is the baseline. And if you look at this term a little bit more closely, what this term is saying is that this is essentially quantifying how much the action ut is better than the average action in that same state, xt. And so following this gradient essentially increases the probability of actions that have returns better than average, and decreases the probability of the actions that have return worse than average. So this is one way of kind of recentering the returns. This quantity is actually kind of so important in practice that it has its own name, and it is referred to as the advantage function. Because it is as if this quantity is encoding the advantage of taking action u with respect to the average action that I could take. Questions here? Yeah.
So the critic is like agnostic of the actor. Like you could, like it's like a model of like actions that you can take in the states. It's like you could swap out the actor for a new one, and keep the same critic, and it would still be representative of the problem. Is that the right interpretation?
I would say so. So functionally, this is just a separate parametric function. So there are two different objects. Of course, the way we fit the parameters of the critic, phi in this case, depend on the policy. Because you can imagine that we will be fitting our critic depending on the experience that we have in our environment. And this experience is dictated by the policy. So I would say this is not independent, because here we're still fitting the value function of that policy, which for us is the actor. Does it make sense? Yeah. Yeah.
Example on how policy might give you an average action and what that might look like for the value function.
So remember that the policy for us is just a distribution over actions, right? So in this case, in the continuous case, it could be a Gaussian over a continuous action ut. Or in the discrete case, it might be, say we have the four kind of cardinal directions again, and these are our actions. The policy might just be a categorical distribution over these actions, right? So what I meant by average action in all our discussions of value functions there on the slide was basically mean we could, since this is a valid, these are valid distributions or actions, we could take the expectations under these distributions, if that makes sense.
Okay, so this is like kind of like a stochastic environment?
This will be a stochastic policy.
Okay, yeah, okay.
Yeah.
Kind of back to his question, but even if it will be a different critic based on like the actor, could you like use like a pre-trained critic so you don't have to like have it start from scratch at the beginning of training, or do you always train them kind of together?
So I think I have two answers. One answer is the kind of theoretically grounded answer. I would say no, you cannot do that. Because this is, so here we're estimating the value function. And remember, the value function is an object that refers to a specific policy. So here we want to use the value function of the policy that we're learning. At least for these algorithms that we're looking at right now. In practice, as long as this quantity here is something useful and aligned for policy updates, for gradient updates, then you might get some benefit in using a pre-trained critic. Yeah. Yeah.
What's the like specific mechanism that you're using to update the phi parameters? Like, is it similar to like Q-learning, or is it something?
Yeah, great. It's a great question. It's coming, I think, in 1 or 2 slides. Short answer is, if you recall what we were doing last week with kind of fitted Q-learning or using function approximators to estimate the value functions, this is exactly the same thing. Yeah, but it's coming in a couple of slides. Okay, and so let's look at, so we introduced actor-critic methods as strategies to try to blend the best of both worlds between policy optimization and value-based approaches. So let us even just visually look at an example of a value-based methods in the top left, so fitted Q-learning, and the kind of V0 version of a policy optimization algorithm that is reinforced, and compare it with what we're doing here with actor-critic methods. So in fitted Q-learning, if you remember, we were, well, of course, running policy in the environment to collect trajectories, and then we were fitting a parametric function of our value function, Q phi, in order to basically solve a regression problem, right? So we're specifying some targets, which could be either the Monte Carlo targets or the TD target. And then we were trying to minimize the prediction error from our parametric approximation and the ground truth target. And this is exactly what we will find in actor-critic methods. So we still run the policy in our environment to generate trajectories. And here in actor-critic methods, we are fitting either a value function or a Q function or advantage function. It'll depend. This is a choice. But we are ideally doing exactly the same thing, right? So in a way, this is exactly the same thing we're doing with fitted Q-learning. Here we're doing in actor-critic methods. At the same time, while in fitted Q-learning, we were using the learned Q function to implicitly define the policy. In actor-critic methods, we are doing the same thing that we're doing in the reinforce. That is, we are leveraging our computations here to define a policy gradient expression and use this to take a step in parameter space. But so I hope that at least intuitively, you're starting to see how we're trying to stitch together different individual components of different families of algorithms. Okay. Now, a question here is, so first of all, we had many examples of using value functions V, using Q functions or advantage functions. What quantity should we estimate and what are the trade-offs? I would say in general, there are no right or wrong answers. I would say different algorithms might just have different implementations of the same underlying idea. But for example, one thing that you might consider is just the complexity of the value function estimation problem. So For example, the value function might be easier because it only depends on states as the inputs. On the other hand, if we were to learn a Q function or an advantage function, we would have to learn a mapping from states and controls rather than just states. I would say probably the most popular implementation of an actor-critic algorithm, which uses the advantage, also refers to as A2C or advantage actor-critic, is something that has this specific choice of what we're fitting. So in principle, we want to use the advantage, which is the Q function minus the value function V. Of course, what we want to do is we want to avoid to have to estimate two objects, right? We don't want to fit two separate networks, one for the Q function and one for the value function. And so the the trick that is typically being used is that we can approximate the Q function as the instantaneous reward plus the value function at the next state. And so according to this approximation, now you can see how the advantage can be rewritten as a function only of the value function V, of the state value function. And so this basically, through this kind of reparameterization here, this enables us to basically fit the advantage or use the advantage in our policy updates while only having to fit the value function, if that makes sense. And so indeed, kind of the advantage actor-critic algorithm, or A2C, is indeed something that runs the policy in the environment, uses those interactions to fit a value function, uses that value function to compute the advantage according to this approximation, and then uses the advantage to in the policy gradient expression. Okay, so now to answer also to your colleague's question. So here we're talking about estimating different quantities and different value functions. How do we do this, right? And the main idea is that we simply leverage exactly what we were doing in value-based methods with function approximation. Specifically, you could do this through Monte Carlo learning. That is, we collect a data set of state and return pairs and basically do supervised learning on these tuples, on these pairs. Or we could use equivalently TD learning by similarly collecting a data set of state and TD target pairs and fit and basically solve a regression problem that fits a value function that approximates and minimizes the error with respect to this target. Does this clarify? Yeah. Okay, so now just as a brief detour, I wanted to briefly go through the AlphaGo paper. First of all, to show you that this is now maybe a few. This is like 2014 or something along those times. But it is one of the biggest successes of reinforcement learning, arguably, and I definitely invite you to check out the paper because I would say that through everything that we discussed today, we actually can understand, I would say, the entire paper, most likely. So starting from, and I just want to highlight a couple of, I think, interesting points. So remember, kind of AlphaGo is basically this project where they wanted to learn through reinforcement learning how to play Go, which is extremely high-dimensional board game, if you wish. The idea here was to leverage, first of all, define you already start seeing a policy network and value network. So here they use an actor-critic method for this problem, whereby the policy is basically something that maps states, that is board configurations, to actions, which is a distribution over a finite amount of next moves in the board. And the value network is basically a parametric representation of the state value function, which similarly maps from current configuration of the board or the state to a scalar number that represents the value of that board configuration. Now, if we skim to how the actual algorithm is implemented, so you will see how, so of course, we train the policy network by policy gradient reinforcement learning. It was learned through self-play. So you could imagine having the policy kind of pitched against itself or previous versions of itself in a simulated environment. And so the games were replayed to determine the policy gradient update, which is defined exactly as we were doing today. Again, the notation slightly changes, but here we are basically discussing this is the update that you do in parameter space as the empirical mean, 1 over m times step size alpha. Here we have the grad log pi's, so the probability distribution of reaction given states, times the z here represents the return, so the return that they observed in the environment, minus the value function of the state v. And here they say that indeed, so they use the reinforced algorithm with a baseline v of st, which is basically the value function as a baseline. And they use this for variance reduction. Again, I definitely invite you to check this kind of the details of this paper, because I would say that vast majority of the concepts here we did indeed cover today. Yeah.
Is there a reward signal, just win-lose at the end of the episode?
Yes.
Okay.
Yeah. Of course, here we kind of glossed over kind of one of the main contributions, which is the search element of this approach, meaning in order to sample from the policy, they weren't just sampling from a categorical distribution of reaction, but they were using that distribution to guide an explicit search process, specifically Monte Carlo tree search. But I would say high-level intuitions from the perspective of the reinforcement learning side of things are exactly the topics we covered today. Yeah.
Was the policy they found like guaranteed to be best, or was it like a human could not be?
No, indeed. So of course, the moment you go for kind of deep reinforcement learning algorithms, there's no theory that kind of can back any of this in terms of proofs or guarantees of convergence. They were able to beat the world champion of Go, and so they claim this as a good enough result for this policy. Yeah. Yeah. Yeah, indeed. Kind of the full picture here is that at the time, they started learning through behavior cloning, and then they basically collected data sets of expert demonstrations, and then they fine-tuned this through reinforcement learning. Jump-starting this work, they actually showed that the behavior cloning part was detrimental to final performance, and they just learned everything through self-play. Yeah.
Sorry, the last question, but you mentioned that every 500 iterations, it re-updated the one that it was training itself off of with the parameters that it found worked the best. Do you know if there's a way that they avoided it, like converging on some policy that just like won over those parameters that the other one was playing with, if that makes sense?
I don't
Or is that like part of the search policy?
what they were doing.
Okay.
I mean, the intuition there is that you want increasing level of proficiency also for your kind of adversary, if that makes sense. I don't think, I'll have to double check, but I think that just by the fact that you are updating your adversary, and you have kind of this learning loop that goes around this update, you'll always be incentivized to find strategies that are better with respect to your previous version. And so you're kind of hill climbing in that sense. But maybe they did something slightly more sophisticated. Yeah. All right, so finish this lecture on Wednesday. We'll be also start discussing model-based reinforcement learning methods. Thank you.